So today we're going to cover section 2, and it's on using perpendicular bisector. So the first thing we're going to do is define what a perpendicular bisector is. And it's going to be a segment, a ray, a line, or a plane that is perpendicular to a segment at its midpoint. Now, when we have a perpendicular bisector, what it's going to be bisecting is going to be a segment, because we need to be able to find the midpoint and create two congruent pieces. So this is why it's not going to be bisecting a line. So what your perpendicular bisector is, it's going to be a bisector of a segment. And again, I could say here that CP is the perpendicular bisector of segment AB. Next, we'll see what the perpendicular bisector theorem states. And this states that in a plane, if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segments. And equidistance means the same distance. Talk about this. Okay, so what this means is if you have a point on the perpendicular bisector, so my perpendicular bisector here is going to be the line CP. And the way that I can tell that this is a perpendicular bisector is notice it's got a right angle and that it's split the segment into two congruent parts. And what the perpendicular bisector theorem states is that if you have a point, so point C, that is on the perpendicular bisector, then that point will be equally distant from endpoint B as it is from endpoint A. So I could add congruency marks to this because I know that AC is congruent to BC by my perpendicular bisector theorem. So if you were using this as a reason and a proof, this has a name and you can just call it perpendicular bisector theorem. If I were to add another point, say on the bisector, let's say I call this point E. I could say that point E is equidistant from both A and B, and I could add congruency marks. So the converse states that in a plane, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So as soon as you see the congruency marks, for example, here on the AD and the BD, you're going to know that this point D is on the perpendicular bisector. Because remember, that line keeps extending forever. So I could say that C lies on, so I could, a bunch of statements I could come up with from this picture. I could say C lies on the perpendicular bisector of AB. I could also say that D also, so D is also or lies on the perpendicular bisector of AB because it's got the congruency marks. I could also say CP is the perpendicular bisector of AB. All these statements can come from this picture. We're going to define what it means to have concurrent lines. So concurrent lines are when you have three or more lines, rays, or segments that intersect at the same point. So for example, if I draw three lines here, and they all intersect at the same point, these are called concurrent lines. The point where those three lines meet is called the point of concurrency. So the point where the three lines cross or intersect is the point of concurrency. So now we're going to use that definition that we just talked about, and we're going to look for the point of concurrency, or where the perpendicular bisectors meet. So the concurrency of the perpendicular bisectors of a triangle are going to be the perpendicular bisectors of a triangle are all going to intersect at a point that's going to be equidistant from the vertices of the triangles. So all the blue lines are going to be the perpendicular bisectors. So if I wanted to add little right angles here, and I could add my congruency marks, because remember they're hitting at the midpoints. So all the blue lines are the perpendicular bisectors, and then from there we could draw in all the equidistant segments from the vertices. So in this figure, all of the red lines are congruent. So I can state here that AP would equal CP, which equals BP. And this is going to go from the point of concurrency, where the three perpendicular bisectors meet, to each vertex. And they're all going to be the same length. So the point where these three perpendicular bisectors meet has a special name. And the special name is called the circumcenter. So it's going to be the point of concurrency where the three perpendicular bisectors of a triangle meet. And it's going to have a different location depending on the type of triangle. So when you have an acute triangle, the location of that circumcenter is going to be inside the triangle. When it's a right triangle, the circumcenter will be located on the triangle. And when you have an obtuse triangle, it's going to be located outside of the triangle. And we're going to learn different names throughout the chapter for different points of concurrency. So this is the first one, and it's the circumcenter, and it's where the perpendicular bisectors meet. So whether you come up with a little acronym to remember, like when it's an acute, so knowing where they're located is going to be important for you. So when it's an acute triangle, it's going to be inside, maybe two vowels, AI. When it's a right, it's right on. And then when it's obtuse, OO, obtuse and outside. Whatever thing's going to help you remember where this circumcenter occurs. And again, when you're doing this on the test, if it asks you to locate it, which it probably will, you'll be given a coordinate plane. You'll have to come up with the coordinates of this circumcenter. What I would do is rotate your paper as you're drawing in your perpendicular bisectors. You would have to find the midpoint, draw in your perpendicular line, and find the point where they meet. If you remember that when it's an acute triangle, it's got to end up meeting inside the triangle. This will help you. When it's a right triangle, on the triangle, and obtuse, it'll be outside. So here's some examples. So the first one, it's telling me that BD is the perpendicular bisector of AC. So what I could add here is I know that if BD is the perpendicular bisector, I've got a right angle here. I know this one's congruent to this. And then I also learned that when you have a point, and point D, when that point is on the perpendicular bisector, then I know point D is equidistant from the endpoints. So that tells me that AD is congruent to CD. So to find the value or the length of AD, I'm going to find the value of X by setting 5X equal to 3X plus 14, subtract the 3X, 2x equals 14. Divide by 2. X equals 7. Didn't ask me to just find x. It wants AD. So I'm going to come up here, plug in 7 for x, and the length of AD equals 35. Again here, 2 parts to this question. It's telling me that WX, this line, is the perpendicular bisector of YZ. Let me highlight it instead. So again, I could make it go all the way up because it's a line. Notice that I have 2 numbers here that are the same. So this tells me that point V is on the perpendicular bisector because I have the congruency. I'm jumping to part B. Let me go back and do part A. What segment lengths in the diagram are equal? So already you can see that it was given to you that YV is congruent to ZV. They both have 25. And again, it didn't ask for congruent, it asked for equal. So let's go ahead and change that to an equal sign. We can also tell that because X is on the perpendicular bisector, it's also going to be equidistant from the ends of the segments. So we could also say that YX is equal to ZX. We can also see that point W is on that perpendicular bisector. So we could say that YW is equal to ZW. So those would be the segments that are equal in the diagram. Now, it's asking me, is V on WX? And the way that we could tell that V is on that perpendicular bisector is because V is equidistant from the endpoints. So because YV equals ZV, I could say yes, V is on WX, and what I'm using is the converse of the perpendicular bisector because it tells me that it's equidistant from the endpoints. So I'm using the converse.
What does it say yes and then V?
Yes, V is on WX. I just answered the question. The answer was yes.